Good morning, everybody. Just a reminder to either turn off or silence your cell phones during the presentation. If during the presentation you want to ask questions of the speaker, we'd also like to ask you to queue up at either of the two microphone stands and ask your question into the microphone so that everybody can hear it. It is day 4 of 23C3. It is 11:30, an ungodly early hour. And it is time for a presentation on unusual bugs. Our speaker is a returning speaker, and I will hand it over to him. His name is Ilja, so welcome him. Welcome, Ilja.
This thing on? Yeah, okay. Good morning, everybody. Yeah, so as the Herald just said, it's way too early, and I haven't really slept that much because, you know, day before you still have to finish some of your slides, things like that. So let's just get started. Who am I? My name's Ilja. I love to see things crash and burn and aim for something expensive in the process. Work for a small security company called SureSec. I'm part of a security group called Netric. I have a blog and a website. If you think I'm interesting, you should go there. The things I'll be talking about today. Null pointer references. So first thing I'll talk about, Stack Overflow, shifting the stack pointer, reference counting, issues with reference counting. One particular case of file race conditions where everybody thinks you're doing it right, but you're actually not. Some issues with regular expressions, and then if I have time left, I'll talk about some issues writing to fixed file descriptors in libraries. And then at the end, I'll actually do a tool release. Right, so let's just dig right in. The things I'm going to talk about are not really big secrets, although some people like to pretend they are. Most of these things have been mentioned in one way or form or shape somewhere on the internet, but apparently not that many people have read them, or even if they've read them, they haven't entirely understood them. And I sort of have the same thing, right? Because I do a fair amount of code reviews, and you run into some things and you go like, well, you know, I wonder what would happen if, you know, you do this and this and these things, and, you know, how would this, you know, this particular piece of code react to it? And so, you know, you start looking into these kind of things, and you know, you find some interesting things, and then you do some Google search on these things, and you see that somebody else, you know, at some point in the past has already looked into these things, but it turns out that not that many people actually know about it. I'll have some demos. Actually, I'll have one, because I had another one, but that one didn't get finished. Just to show that, you know, most of this stuff is not really theoretical. And I'm doing this because I've done a similar talk a couple of months before at RuxCon, and people liked it, but they went like, you know, it's all, you know, it's theoretical and stuff. And it's really not, just that at the time, I didn't have enough time to make demos. I'll show you one demo. This stuff is not just theoretical, right? This can actually happen. You can write exploits for these kinds of things. And most of it is ongoing research. It's not finished. There's probably a whole lot of stuff I don't know yet, and feel free to contribute. So null pointer references. I found a quote about this. I'm not going to say the entire thing because it's way too long, but this was said by one of the Opera browser developers, and at the end he says, you know, ordinary null pointer crashes that have no possibility whatsoever to be abused. He's wrong, and I will tell you why. So as this guy as I just showed you in the quote, most people consider null pointers to be non-exploitable, right? Because the address that you're referencing is usually not mapped. And so people go like, well, you know, at most there's a denial of service. You know, if it's local in a browser or whatever, it's not even a denial of service, right? It just blows up and that's it. So first of all, if you have a null pointer reference, sometimes you don't even need this particular page to be mapped. There's basically two cases that I've come across where you would have some kind of issue with a null pointer and where the page doesn't actually have to get mapped. The first one is where you get your null pointer and you add some offset to it where you have a lot of control, you know, where the offset's really big. And then you get to write to, then basically the offset will get used as an absolute address. And the second one is basically where you have a null pointer of, you know, that came back from some, you know, malloc or whatever, and where it gets passed to another function where null has some special meaning. And one example is strut_doc_r. And I'll give you two examples of these things. This is one, I know it looks ugly. I've already tried to clean this up. It comes from procmail, so you know, I've done my best. So basically what's going on here is they basically call this function where they add a byte to a piece of memory. And so they have some bookkeeping where they see, you know, if this byte doesn't fit in memory, we'll reallocate, and then once we relocate it, we'll use this offset from our bookkeeping inside this chunk of memory and write our byte to it. And basically, so yeah, these two functions here basically get called this thing here, and these functions get called from within procmail. So basically what this does is, if it's the chunk they want to write to is not big enough, they reallocate. And the problem they have is they don't check the return value of realloc. So it can return null, right? If there's not enough memory, it'll do that. And so they do null, and then they add this offset to it, which is in their bookkeeping. And then, you know, they use the offset as an index, and then write your byte to it. So if realloc fails, this offset really actually becomes an address instead of just an offset. And so basically, if realloc fails, you get to write to some piece of memory you're really not supposed to write to. Basically, user-defined byte. And this one is, you know, as far as I've seen, pretty much exploitable. It takes some poking, though, because it's not that easy. The second case is where, you know, you pass a null pointer to a specific function. And this particular piece of code, which is also quite nasty, comes from X. You know, you wouldn't expect this because, you know, X is known for their code quality. So this is another case where, you know, they do some kind of memory allocation and they don't check return values used. And so in this case, it's a string duplicate, which is basically just a wrapper around malloc. And then, so SP namelist can potentially be null, a null pointer. It gets passed on to this thing called struct_r. And this function, struct_r, has this special casing where if the SP namelist, in this case, is null, instead of using SP namelist, they'll use talk_last. And so the thing that struct usually does is it takes this argument and scans this string, and then if it sees it, it changes it with a null byte, basically, because it splits up a string, right? And but in this particular case, if this thing is null, it will use this pointer. The problem being that the first time you call it, this pointer is actually not initialized. So if you get this special case where you get null, but this pointer is not yet initialized, then this pointer could potentially be anything, right? It's just a piece of uninitialized memory. In this case, it's on the stack, right? So, you know, with some fiddling around, you could sort of define that. And so basically, you get to make this thing an arbitrary pointer and then get some memory corruption done, because if it looks for a string and if it from that where it points to up until a null byte, and if it sees any column, it will just override it with a null byte. So I've described the steps here, basically. And if it overrides it with a null byte, that's basically memory corruption. This is bad because, you know, we've seen this before. It leads to code execution. Right, so those are the two cases where you don't need your null page mapped. People know these things, but these kind of cases are somewhat rare. They happen, but they're rare, and they're usually fairly hard to spot because it's usually in ugly code like procmail or X or something like that. Let's not talk about these two cases, but others. If you think about null pointers, null is just another address, right? It's 0x0000 basically, right? It's a valid address. There's no universal rule that says this page can be mapped, right? It can be mapped, it can be there, it could be used, right? Perfectly if it's in your virtual address space. So the question is, how can we force an application to map this page, you know, and force it to map it before this application dereferences a null pointer, right? So in what context can we do this? And it turns out that these things are a little bit operating system specific. Talk about some cases. There are some cases I don't know yet about, or haven't looked too much into it, but I hope this will satisfy you. So the first case I looked at is it's mapped by default. It's already there. There's data on it. You could use it. The page is at least readable and there's some kind of data on it. Turns out that somebody had already written exploits for something similar like this about 12 years ago. So, this is one of these cases where you go look for something and, over a decade ago somebody else did this too. And it's done by a group called 8LGM, who were madly skilled and did some really awesome stuff in the late 80s and early 90s. And so they had this exploit for SCU Unix, and so you can see it was done in 1994, and they basically, they have this hilarious bug. You can read it if you want to. And basically they say, if your operating system maps it by default, which, SCU at the time used to do, then you can just read or write, I think in this particular case, only read from this page. But in this case, it was more than enough. So this was the first publicly documented null pointer reference exploit I could find. So, and I don't really know any operating systems today that map this page by default and give you some attributes where you can at least read or write it. Maybe SU still does it. I have no idea because, I don't use, Unixware, OpenServer, or any of that kind of thing. So, let's look at the second case of where you could potentially exploit null pointers. The kernel, your kernel. And this is usually in where you're in kernel mode but still in user context. And depending on your operating system and your architecture, if you're in kernel mode but user context, your virtual address space is shared. So the kernel can basically just reference your virtual memory directly without, doing some kind of weird transition. And so this means that if the kernel has a null pointer, before you trigger it, you could just map it in userland and then trigger it in the kernel, and it will actually use the same null page that you just allocated. And the way you allocate a null page in Unix is you use mmap, and you specifically give it a flag which says, so the first address is first argument is usually the address, but in most cases this is just a hint, right? So people usually don't set it. It's just, if you have it available, please give it to me, but it's not a requirement. And so usually what you end up doing is people just in the kernel, this argument gets ignored. Unless you say map fixed, and then it says, give me this address or fail. And so if you want to locate the null page, you say, give me the null page or fail. And most operating systems that I've tried it on, Linux, FreeBSD, OpenBSD, NetBSD, and a few others, they allow you to map the null page. There's no specific rule that says you can't do this. If you specifically ask for it, you get it. And so this is, you use mmap to basically map it. Of course, exploitability still depends, right? It depends, like if the kernel has a null pointer dereference, it depends on what it's doing with it. If it's just touching the page and reads some dumb value of it but doesn't do anything else from it, you might get a kernel panic out of it, but that would be it. On the other hand, for example, if they use it and they think it's some kind of structure which contains a function pointer, and then they would execute this function pointer, well, then these kind of things become exploitable. So a lot of them are exploitable, some are not. The large majority of them are. And so I'll give you a demonstration of one of these bugs in the latest version of OpenBSD. This is, let's see if this gives any better. Okay, so you can see, well, it's pretty small. I hope you can read this. Basically, it's OpenBSD 4.0. I call it foo.mydomain. My ID is 1000. That's my user. Now I will run my super cool exploit, which I called blah. And now you're owned. Right. And this is basically a null pointer. And so this is basically a null pointer reference in the OpenBSD kernel. Ooh, well, Okay, so that was the demonstration, and I'm really glad it worked. The exploit's kind of stable, but usually when you're on stage, things have this tendency to blow up in your face. So I'm glad it didn't. Right, so basically what's going on is like, I actually found this bug, not by doing a code review, but I was working on a fuzzer for Unix, and I'll talk about it later. And anyway, when I was fuzzing it, eventually I hit this kind of bug in OpenBSD, and so that's in this function called AGPIoctal, and what they end up doing is they call AIX and some offset into it, and they reference it. And so I wonder what AIX would be. Oh, look, it's a null pointer. And so what we end up doing is you map this page and you put a function pointer in there, and the kernel eventually calls it. So yeah, this one's exploitable. So that was the kernel. This was a demo. So this is not just theoretical. This really happens. You have to watch out with these kinds of things. So what about userlands? These things are, as it turns out, a lot more OS dependent than the kernel. In the kernel, we can still make some assumptions. On most architectures, we'll have this shared for address space, and you can map it. And so, it's not always true, but usually it is. In userland, it depends enormously, depending on the operating system you're using. Your goal is still the same. You want to get an application to map the null page before it does any kind of null pointer dereference. I did most of my testing on Linux. I would assume there are similar cases in other operating systems, or maybe totally different cases where you can still end up getting a null page mapped. I did most of my testing on Linux. So first of all, in early 2.6 kernels, I think 2.6.9 till 2.6.12, they changed the way a userland application would get memory from the kernel. And basically, I think they call it a, top-down allocator. And what that means is, I'm just reading this of LKML, right? I didn't make this stuff. But apparently what this means is that you start off with a very high address, in this case 0xbf something something something, and whenever you allocate memory, the address becomes smaller and smaller and smaller, and you go all the way back to the null page, including the null page. So what this really means is, if you have an application where you can get it to allocate arbitrary amounts of memory, eventually it will just map the null page, right? And so, you start thinking, what application could you, possibly get to allocate arbitrary amounts of memory? Oh, look, you have this browser, and, the more JavaScript you put into it and the more memory you allocate, it will happily do this stuff for you, right? So, if you're using one of these kernels and you think Firefox has a null pointer reference in it, be very scared. We're talking remote code execution here. Luckily, though, so this was actually talked about at a conference earlier, I think CanSec last year, and the kernel guys saw this and they're like, holy crap, something's horribly wrong, this can be abused, let's fix it. So they fixed it in Linux kernel where they would use this, basically they would keep the same memory allocator, but they would specifically exclude the null page from it. So if you would do this allocations and you would eventually get to the null page, it will just tell you you're out of memory. Bad luck, crash or whatever. But they basically said that they're still going to allow map fixed, which is good because that means you can still exploit kernel null pointer references. Because, right, you want that, right? And this was done. This was actually done by Linus Torvalds himself. So, if this doesn't work anymore, let's see what other options we have. Turns out on Linux, you've got this thing called personalities, and what that means is that you can say, hi, I'm an OpenBSD binary, or I'm an HP Unix binary, or I'm an SCO binary, or something like that. Emulate stuff for me so that I can work. This is called a personality. And one of these personalities is called SVR4. And for some odd reason, SVR4 binaries have to have the null page mapped, because if they don't, they go up in flames. So you say, hi, I'm an SVR binary, map the null page for me. And so what's really interesting about this is that these personalities, they get inherited through, every time you execute a new application, they get inherited. So as long as you don't change them, they stay the same. So you can say, hi, I'm an SVR4 application, and now I'm going to, run SU, and SU will be an SVR4 application as well, and the kernel will locate a null page in, for example, SU. So if then you have null pointer reference in SU, they might be exploitable. Let me get to that in a second. So these personalities get inherited, and this is basically the kernel code, and they basically say, why in the hell would you want to do this? Because SVR4 needs it, and if it's not there, it blows up. So, and that's why it's there in the kernel. And you can just call this, right? It doesn't do any kind of privilege check. You can do this for any application you want to, whether it's SUID or not. Right. So there's a downside to this feature in terms of exploitation. The null page is read-only. It's only null bytes on there, so it kind of limits the options. However, there's some good news. If you have 0x0000, you can see it as an alternative no operation on Intel, with the exception that AIX has to point to a valid address. They don't change it, but it gets referenced, so it has to point to a valid address. That's the only sort of constraint you have. So this thing can still be useful if you combine it with I talked about earlier, because you can get it to map the null page, and then you might be able to do a lot of allocations, and they would still locate the page right after the null page, right? And so if you'd have a function pointer that's set to null, it would go to your null page, which has all these nulls, which are alternative null operations. And the entire null page will just be knobs, right? Goes to the second page where you do have control over it, and you'll have your shellcode in there, right? And so these things sometimes help in exploiting null pointer references. There are constraints. Sometimes this is enough. Right. So the last piece of null pointer references. Some operating systems also map the null page by default, but they don't allow you to read it or write it or execute it. So it's pretty much just there because they want it mapped, I guess. I don't know why. But it's useless to us because we can't touch it. It's there, but we can't touch it. There's one particular corner case which is exceptionally rare that I've been told they exist, where you have a null pointer reference, and before you actually do anything with it, they pass it on to mprotect to change the protection bits on this page. I've never ran into them. I've been told they do exist, these kind of bugs. So sometimes in exceptionally rare conditions, this happens. Okay, so the next one is, this was null pointer references. The next one is Stack Overflow. So I went out and, started looking for another nice code I could use for Stack Overflow. And so there's this, principal software developer for a company called Micro Focus. And I think this was supposed to do bug track, I agree that recursion overflow doesn't look like a very promising area for vulnerability research. And I'll tell you why he's wrong. People, as with null pointer reference, people go like, well, this is just another denial of service. But really it's not. If you think about it, a Stack Overflow is really just another overflow. You have a piece of memory, in this case your stack, and you write more to it than you're allowed to. This is a security bug, right? Writing more memory than you're allowed to is generally considered to be bad. So it's another overflow. The question you have to ask in order to get these things exploited is, can I force this application to map important data right after the stack before you cause Stack Overflow? And again, this is a question of context. And again, it's really operating system dependent because the ways you want to try and force an application to map these things are really application dependent. But locally, the odds are in your favor because you control the entire environment. You can say, I want my stack to only be this big, or I want my memory allocator to specifically use mmap instead of break, and then maybe it starts allocating pages right after the stack instead of somewhere else or whatever, right? So chances are, if you're doing this locally, that you can end up really exploiting these things. I did most of my tests on Debian stale. So Felix told me that you write it Debian stable, but you pronounce it Debian stale. So that's where I did my tests on. And this is an older version of the 2.6 kernel, where mmap data is not yet the top-down locator, but they still have where it grows towards the stack. And it turns out that in the Linux kernel, there isn't a guard page between the stack and the heap per se. So what this means is if you can do enough memory allocations, eventually the stack and the heap are just right next to each other, right? This is stack, and you move one byte to the right, and oh look, I'm in the heap, right? Something like that. So basically, if you can allocate enough memory on the heap, and you get a Stack Overflow, you just end up writing into the heap, which is kind of bad, right? So that's a general case in Linux. Threads are something else, though. These are not really up to, in general, so there's a system call to do threads, but you don't want to do that because that's very operator independent. So you have an overlapping library called POSIX threads, which are, really well engineered and not over engineered, and they work exceptionally well, and there are no issues with that. But still, they're pthread implementation specific, these kind of things. And so what you do is you tell your kernel that, I want to be a thread, and this is going to be my stack, and use it. And then your libraries is responsible for either allocating or making sure you get a guard page or that you don't have them. So it depends on your library. I don't know outside of Linux because I only did Linux. Older glibcs do not give you a guard page. So what this means is if you have 2 or 3 threads, their stacks will be right next to each other. So if one of your thread has a stack overflow, it will write right into the stack of the next thread, which is again a really bad idea. Newer ones do. Newer versions of glibc, I think 2.2 or 2.3 point something, they have guard pages. So you would think that kind of stops these things, but it doesn't always stop them, right? You might have a function that looks like this, this here, where you declare a variable on the stack, which is as big or bigger as a guard page, and you end up not using it. And then you call some other function, and that means that you sort of just jumped over the guard page. And you might think that these things are not as common, but they actually are, because and maybe not you see these. Maybe you might not see these things in the actual application code. But I started digging around in libc code, and there's actually a lot of functions, at least in glibc, where they have this huge buffer on the stack, and then they don't use it, and they call some other function, and that function calls some other function. So if you could call any of these functions in one of your recursive functions, you could basically use or abuse your libc to jump over guard pages. I haven't actually tested this, but it looks promising. Again, the kernel. Always with the kernel. Most in kernel stacks don't have guard pages because it's a waste of virtual memory, right? You can have an almost arbitrary amount of, these days anyway, an almost arbitrary amount of kernel stacks, and let's say if you'd have 1,000 and each one of them would need a guard page, then you're wasting huge amounts of virtual memory. And that might be okay on like 64-bit architectures, but it's a horrible idea in 32-bit architectures because the kernel usually only has very little virtual memory that they can actually use for memory allocations and in 32-bit architectures these days. So if you can, basically it's the same thing applies. If you can force some allocation before or after your kernel stack to be mapped, then they might become exploitable. Depending on whatever architecture you use, it's before or after. So I did a few tests on Linux, nothing that extraordinary, but it turns out that this is actually quite easy on Linux. And I didn't have to look far. Somebody else already did this for me. It's this guy called Polstar Zets. He's a Polish guy. He's exceptionally clever, and he's done a lot of Linux kernel exploits. And so in one of them, he needed to have exactly the same thing that I wanted to have, is he wanted to have something after or before your kernel stack that you could smash into. And so, as it turns out, the Linux kernel basically has sort of a pool of kernel stacks. And so he worked out this way where he can basically say, if I'm this process and I want to smash into something after my stack, then if I do this, this, and this, which he describes here in short, then I can exactly determine what will be right after my stack and see exactly what I want to overwrite. So this works fairly reliably, this method. Although I do think that this particular method actually requires AOut to be used, and I know recent 2.6 kernels actually don't have it on by default anymore. So you might have to look into a few, change some of the details. But the basic idea is sound, basically, right? So what you do is you have 3 processes in userland, which have 3 different kernel stacks. And you core dump one of them, and in this core dump, it will actually have your task structure from the kernel, and you can look at its parent and sibling pointers. And if you see that they're right next to yours, or right next to each other, then you know they're right. Then you know that there's something. You know exactly where they are and that they're right next to each other, right? So that means that you can now have one right into the stack of the other. And what's interesting in Linux is that kernel stacks are right after your task structure. They're right next to each other, right? There's no page in between. So this means if you would have a recursive stack overflow in the Linux kernel, eventually you end up overriding somebody else's or your own task structure. And so in your task structure, it contains things like your UID and your saved UID and your groups and effective UID and all of these things, right? So if you have these kind of things, you all of a sudden get to change your UIDs to whatever you want them. So that's kind of bad. That was recursive stack overflow. The next one will be shifting the stack pointer, where I get to bitch on the C standard and alloc A. Basically, if you want to dynamically allocate any kind of array on the stack, there's sort of two ways to do it. So the first one is I guess it's called in C99 standard, dynamically allocating arrays on the stack, and this is basically how you do it, right? You have to function with the length, and you just declare it like this, right? And I think this, is for C it's kind of weird because you usually don't do this kind of thing, but the C99 standard allows for it, and so this sometimes works, and I'll tell you why later. And then the second one, which basically does pretty similar things, is alloc A, and it's sort of. And the cool thing about alloc A is that it looks like it's malloc, but you never have to free because that happens automatically, right? The problem with alloc A is that it's really difficult to actually implement it right. And the actual alloc A man page says this and says, well, you really shouldn't use alloc A because it's compiler and machine dependent and probably even operating system dependent, and it's really buggy on most systems. It's use discouraged. And what they really mean is it's really buggy on almost all systems. And I'll tell you why in the next couple of slides. So this is basically how you use these functions, right? They're pretty straightforward to use. That's how it works, right? So the problem basically becomes is what really happens if you do these things is basically you just locate more space on the stack, and what this really means is that all you have to do is sort of modify the stack pointer, right? Because that basically gives you some piece of memory on the stack. And that's what your compiler does. It generates code that does nothing else but basically just subtract an arbitrary amount of length from the stack pointer. And the code generated for alloc A and these C99 dynamically allocated arrays on the stack are identical. They do the exact same thing, right? And it's only 4 or 5 instructions, and they're exactly the same instructions. No error checking is done. What that means is if you have an unbounded alloc A call, you have full control over the stack pointer. And that is really bad. That means you're owned, right? If they're not unbounded, so if they're bounded, it can still be problematic because they might be very long strings, right? If it's something on your control and they use the length of a string or something, it might still be bad because it might not fit on the stack anymore, right? It would just modify the stack pointer without checking for stack overflow. So you sort of end up in the problem that I just talked about, even if it's not unbounded, but it's really big. Things, problems might still occur, right? You might get stack overflow. So depending on what context you're in, these kind of things might still be exploitable or might not. I don't know. And so I went looking for a piece of code that, gives you these things, and this thing comes out of the Linux kernel. This is a right hook, and so the counting used there is basically, the value you give to write. And up until not too long ago, that was totally unbounded. And now it's sort of bounded. It can be up to 2 gigabytes, so up to like 2 billion something. So it's sort of bounded, but it's not bounded enough. This thing's exploitable. This is really problematic. Well, it should be, but this is PA risk specific code. So there's maybe 2 or 3 people in the world affected by this. So yeah, so basically the problem is compilers are just, so alloc A is basically an inline function, right? So it's not really calls anything, it just adds the assembly code in there. So the code for allocating dynamically sized arrays on the stack are identical, and compilers they put very dumb code in there. It doesn't check for anything. And so I've tried this with GCC, and I've used the Sun compiler and the Intel compiler, and they all do the exact same thing. It's 4 or 5 instructions. They just modify the stack pointer without doing anything. Here's the shocking thing. Microsoft does it right. Hey, you know, they've invested all of this time and resources in security, and it's paying off. So with alloc A, what they do is if you give it some length, they probe every page. So it's slower than what you would do in you know, GC or stuff, but it buys you stability because they probe every page, and the moment they find a page that's not mapped, basically they just throw an exception and say, you know, this thing blew up, handle it correctly. And of course, that's the cool thing with Microsoft's Visual Studio is that it's not really C or C++, it's their own mix, and that means you can have C with exceptions or C++ without exceptions or whatever kind of strange mix you want. But it works out for alloc A because it can just throw exceptions. And what's even better is they don't implement C99 dynamically sized arrays because honestly, it's a horrible idea. So, and I bet, you know, somebody at the Microsoft compiler group, they read C99 spec and he's, you know, oh, there's dynamically sized arrays on the stack. They must have been smoking crack when they wrote this, right? So they don't implement this, and because you don't really need this stuff, right? Look, if you want to dynamically allocate memory, use the heap, right? And the punishment you get is that you have to call free. That, you know, that's your punishment for wanting to have dynamically sized arrays of any kind, right? So just use the heap. They're meant to do these kind of things. The stack is not. Right, so that was shifting the stack pointer. Next thing I'll talk about are reference counting issues. And so basically I found this other quote from somebody in Mozilla who realized the exact same thing. I'm not going to read it again because it's way too long. But if you happen to run the slides later, this pretty much explains the entire thing. So basically, reference counting is sort of a way of memory bookkeeping. And so it's sort of or at least it seems like it's an easy way of memory bookkeeping. So what basically happens is you can have certain objects, you know, in memory, and people would reference count them. And you do this so that you prevent freeing objects while you're still using them. So what basically happens is, you know, if you have some kind of function which takes this object and uses it, it increases its reference counter. And then when it's done using it, it decreases it. And when this object's reference counter gets to 0, it gets freed. Because that means nobody is using this stuff anymore, and it's safe to free it. Well, this sounds easy and you know, easy to do. Turns out it's actually not. Because you sort of have to, for every case where you use an object, you have to basically do 2 calls, which is increase reference counter and decrease it. And it turns out that in specific error cases, it's really difficult to keep these things balanced. Or, well, apparently it's difficult because everybody keeps making these mistakes. So one of the most common mistakes that people make is they use the object and they increase the reference counter, but in some error code paths, they forget to decrease it. So what this means is the reference counter, you know, before you got the object, might have been 1, and then, you know, you use it, so you say +2. And then you forget to unuse it, right? You get to say that, you know, you don't want this stuff anymore. So the reference counter stays at 2. And then the next time you call this particular code path, the exact same thing happens. The reference counter goes to 3, and it goes to 4, and it goes all the way up to the maximum limit of whatever integer this reference counter is. If it was an integer, it would be 0x, ffffff. And then the next time you call this thing, it increases it again, and oh look, you get integer overflow. It starts counting back from 0 and goes to 1 and 2 and so forth. So it's sort of a special case of integer overflow. And so I've sort of made a demonstration for this because I hope this makes it clear. So what basically happens is, you know, you would have something let's say an object, in this case a file structure, right? So you open a file and you duplicate it. And what usually happens in most Unix implementations is if you duplicate a file descriptor, you still end up with only this one file structure in the kernel, but a reference counter goes up. And this is to save memory, right? Because if you would actually really duplicate memory blocks for every time you do a file duplicate in userland, you end up wasting a lot of memory that you really don't want to, right? So the reference counter goes to 2, and then you call some function or some system call. In this case, I've called it Rev Counter Overflow because kind of makes it easier to demonstrate this thing, where you call this thing and it increases the reference counter, and then it forgets to decrease it and does it again and again and again. It goes from 1 to 2, 3, 4, 5. The maximum limit, excuse me. So the maximum limit goes back to 0, goes back to 1, stops. So what you end up with is you still have 2 file descriptors pointing to the same file structure, but the reference count is off. It's wrong. It should have been 2, and it's actually 1. So what this means is so you now close one of them. So normally, so what this means is the reference count gets decreased by the close. And these memory functions, these memory bookkeeping functions go like, oh, look, your reference count is 0. I get to free this object. Unfortunately, you still have one reference to what used to be your file structure, and, well, it's now free memory. So you sort of, with these kind of bugs, you end up sort of being able to read or write to free memory, or memory that's supposed to be free, and that's usually really bad. Right. So I have another example of this stuff. This is from NetBSD. This is sysfsync range. I have no idea what this thing does, but I do know that it has a reference counter issue in it. And so what really happens is, so they call this thing called get vnode. And it gives you the file structure of a file descriptor given as an argument to the system call. And vnode basically says, oh, I want this file structure, which is sort of an object, right? And because I want it, I'll increase the reference count. So they basically get vnode internally calls this thing called file use. And then the file descriptor set instead of 1 to 2, for example, and then some non-interesting stuff happens. And then they check this thing called flags, which you have full control over. And they're like, well, if it's not exactly the way I want it to, let's just bail out and not do what you want it to do. And so they basically return from the system call without decreasing the reference counter. Decreasing the reference counter is basically where you use file unuse. So if you would call this particular system call 4 billion times and then somewhat, the reference counter goes to 0x ffff, and next time you call it, it goes to 0. And then it might go to 1 again, and 2, and so forth. So, but the thing is, you probably want it to be at 1, because the next time you would, you then have, as seen here, you'd have a duplicate copy, you'd close one, and you'd end up pointing to free memory. Right. So this sort of issue has sort of an evil twin, where instead of forgetting to decrease the reference counter, you decrease it twice. And these kind of bugs are pretty rare. They're usually in horribly ugly code paths where you have go to error out, and then you go to something else went wrong and go to something else, and then nobody can really follow all these go-tos, and you end up with, for example, double decreases. They're somewhat easier to exploit because you don't really have to sit around and wait for ages, right? Because in the previous case, if you have to wait for reference counter to overflow, it takes like hours, or it might even take days, right? So, but you don't really want that, right? Because it takes ages, right? I mean, who wants to sit around and look at a screen for 10 hours in order to get a root shell, right? So with the evil twin here, you don't have to do this. It's instantaneous, right? Because a double decrease in the reference counter this basically means that the reference counter should have been higher than it should have been higher, but is not. So you could just free something and still have references to it, right? So this kind of thing is really bad. The exploit can be instantly, right? This is like a fraction of a second to exploit these kind of things. Right, so interesting suspects if you want to look into reference counting issues. Most kernels have interesting structures or objects that use reference counting. Things that come to mind instantly are VM areas and files, and there's probably a whole bunch of other things. The X server does some reference counting of some structures. There's Mozilla Xpcom, which is apparently a really ugly clone of Windows COM. Because, you know, the Mozilla guys thought, you know, this is a really nice way to do programming. Let's have Xpcom, right? Obviously, there's DCOM and COM Plus from Microsoft, which I've been told have some, or used to have some reference counting issues. JavaScript. JavaScript apparently does a lot of reference counting of a whole bunch of objects behind your back. I don't know this for sure because, you know, I try not to look at browser code, but I've been told by some browser developers that this is the case. And then apparently Python relies on reference counting for all sorts of things. I don't know this either because I don't like to look at Python internals because my eyes start bleeding. And there's a whole lot more of things, potential, you know, huge programs where you might get reference counting issues. Right, the next one is, so special case of file race conditions. And this one's, I find it rather interesting. So you sort of have this case in Unix where you have an SUID where you want to sort of try and safely reopen a file in a publicly writable, world writable directory. And so people have known for ages that it's difficult to do these things, but at some point somebody stood up and said, this is how you do it in a safe manner. And so what they've come up with is what I call the lstat open fstat dance, where basically you get a file name of a file that you want to safely reopen in a publicly writable directory. And before you open it, you call lstat on it. And you call lstat because lstat doesn't follow symlinks, and that means you can instantly see if it's some kind of symlink, then it's probably bad and, you know, bail out. Right? And then you still keep the stat structure in memory. You call open, and before you do anything to this file, you call fstat on the file descriptor. And then basically you compare the stat structure of fstat with lstat. And people, you go like, what people basically do is, if they compare the stat structure and they see if it's this exact same inode number and it's on the same device, then it must be the same file and we don't have a race condition. Unfortunately, this isn't true. There's still a race condition, and this is because between the lstat and the fstat, you might still be able to delete this file and create a symlink to something else, which just happens to be on the same device and has the same inode number. Because you remove this file which had this inode number and device, and then you might be able to create another file which is on the same device and gets the exact same inode number because the inode number just got freed because you deleted something, right? And so apparently people haven't really picked up on this yet. So this means that there's still a race condition and that using this lstat open fstat thing is still insecure and you should never do this. So, you know, I've talked to this about some people and they go like, no, this isn't true. If you compare more structures from the stat structure, then it's totally safe. You know, don't worry. We've seen all these things. It's completely safe. But it's not. And so here's the entire stat structure. And I'll walk over them one by one and see exactly what they do. And then you can sort of see, well, you can spoof all of these things. Well, sort of, you know, or fake them, right? So the first one is it has to be on the same device. Well, okay. That's usually not really a huge constraint. It could be, but it usually isn't. It has to be the same inode number. It's a bit annoying, but depending on the file system, it's usually realistic to delete a file and then create an arbitrary other file with the same inode number on the same device. It takes some work, but it's realistic to do this. Has to be the same mode. Okay, it's a constraint, but it doesn't prevent the race condition. It has to have the same amount of hard links. Well, who cares, right? Has to be owned by the same user and group. This might eliminate some cases, but it doesn't stop the race condition, right? It's still there, and I'm sure there's a bunch of cases where it's okay to, you know, where they compare the UID and GID, and where it's okay if they match. the next one is basically where the file has to be the same size. I guess this, again, this might be a problem in some cases, but it doesn't prevent the race condition. And then the block size doesn't really matter because it's usually the same for all files across one file system. The block count is sort of like the file size, but it differs if you have sparse files. So again, this does not prevent the race condition. And then so basically you get the file timestamps. And so people kept telling me, compare the file timestamps because that's what makes it secure. That prevents the race condition. So I started thinking about this and like, well, these are time t's, and time t is the time measured since epoch. And epoch is January 1st, 1970, right? They're measured in seconds. Computers are really, really fast these days, and I bet I can win a local file race condition within a second. So even if you compare these things, they don't really add that much, right? And if you fail within that second, there's not really a problem because you can just try again and again and again until your race works within that one particular second. So you get a whole second to race. Depending on the way you mount your file system, a time doesn't really matter because it doesn't get changed. And then if none of these things help, you can just wait for 70 years. Time t's overflow, right? I think 2038 or 36 is when it starts overflowing, right? So if you have enough time on your hands, just wait for a while. So if you're an attacker, you're in luck because if people would compare all of these fields, it wouldn't prevent the race condition, but it would make it really, really, really difficult for you as an attacker. People usually don't compare like all of the fields because who would want to do that, right? They usually just compare the inode number and the device. Sometimes they look at the number of hard links. Sometimes they look at the mode. I haven't really seen anything else besides that. So if you're an attacker, you're in luck. If you're trying to write code that safely reopens a file in a publicly writable directory, I have bad news for you. You can't do it. It's impossible to do it safely, as far as I know. So somebody else came up to me and said, well, you can prevent this race condition by, if you call open, say, oh no follow. And what oh no follow means is that it won't follow a symlink. Unfortunately, this particular person was wrong because you don't necessarily have to have a symlink, right? Because the case basically that the whole case of this thing is if it has the same sort of attributes, it must be the same file. But it's not true. It could be a totally different file, right? The symlink is basically just a way of easily exploiting these things, right? So using onofollow, first of all, doesn't prevent the race condition. There's still a race condition. Second of all, onofollow is really not what a lot of people think it does, right? It actually does follow symlinks. It just doesn't follow symlinks at the end of your path. It follows directory symlinks. It does not follow file symlinks. So there's still cases where even onofollow won't save you if you use a symlink. But in a general case, onofollow prevents an attacker from using a symlink, but that's it, right? So let's say you might be able to use a hard link if people forget to check for the number of hard links in their check. And even if they don't, you might be able to force an application to create the file with the exact same name and the exact same inode number and the exact same device, but with a totally different content. So yeah, file race conditions. So basically, safely reopening a file in a world writable directory is impossible. Don't try it. There's piles and piles of vulnerable applications that do try it. Audit them. You'll find lots of cool bugs. Trust me. So moving on to regular expressions. Regular expressions are often used for input validation. And if they're not used for input validation, they might still be used for some kind of pattern matching in security-sensitive context. Snort, for example, right? The thing with regular expressions is that they're this odd-looking things, and nobody really knows all the details of how these things correctly interact with each other. So it's really hard to get regular expressions exactly right. They might look like they pass whatever you give it to, but there might be some corner cases that you're not aware of. Even really simple regular expressions are not always what they seem. So I ran into this thing in a web application where they wanted to get some number as input, and that was it. They didn't want anything else. Because this would have gotten written to a line-based configuration file, and if you gave in something else, it might be horribly wrong. So they use this thing where they end with a $, and they start off with this sort of hat thingy. And I have no idea what the caret is called, so I'm just going to call it the hat thingy. Do you know what it's called? The caret? Okay, so it's the caret. Thank you. And so it's sort of the caret and then a few numbers, dash, a few more numbers, and a $. That's it. And so what this means is basically I want to have a line which is just that and nothing else. If there's anything else in there, I'm going to fail it. It won't match. And that usually works, the problem being that the $ also matches the next line. As it turns out, in this particular web application where I found this thing got written to a line-based configuration file. So you get next line injection, and that was kind of catastrophic. Well, hey, I did some Googling for regular expressions, and I have no idea what this thing does, but it looks horrible. So if it's difficult to get this right, nobody can get this right. Right? And somebody else also wanted to make a huge regular expression, and he couldn't get his regular expression compiled by GNU regex because GNU regex has actual limitations on the regular expression used. The string can only be 65,000 characters long, and you can only have 255 pairs of brackets, and a few other things, right? If you're hitting these kind of limits with a regular expression, then it's not the problem of the regular expression engine, it's your problem, right? Regular expressions should really not be this long. It's insane, right? Apparently people do want to make long regular expressions. I have no idea why. So these are just some usage issues with, these were usage issues with regular expressions. Now it more comes down to the implementation, right? Some regular expression implementations are not binary safe when they're matching stuff. What that means is for example, the PHP erec function is not binary safe. And what that means is you take a piece of input, untrusted inputs from a web application, and you use it in your erec to match against something. But it's totally untrusted. What this means is there could be 0 bytes and whatever in there. And PHP erec, the erec function, basically doesn't really do anything besides pass on all the data it gets to a C API. And C has this notion of how strings have to work. And strings end the moment you see the first 0 bytes, right? They don't really care what's after it, right? The first 0 byte you get is where the string ends. So you give in this huge string into PHP, but for example, you give the first part of it is something that matches the regular expression, and then right after it you add a 0 byte, and then you add whatever stuff you want that might not match, right? And so erec passes this on to, passes on to the C API, and the C API goes like, oh, this thing matches, and it goes back to PHP, and then PHP says, oh, let's put this kind of this string we got from the user, which now matches, A to Z or something like that. Let's put this in a SQL statement and pass it on to Oracle or whatever, right? And that's obviously problematic because the PHP erec function didn't really match everything, and there might be SQL injection or something similar like that in there. And turns out these kind of things have actually happened, and there's this sort of pen testing group in Germany called Red Team Pen Testing, and they found some of these issues, and I found this to be really cool. More issues with regular expressions. Some people apparently think it's reasonable to take an untrusted regular expression as input. I think this is bad because regular expressions were never built to handle untrusted input, right? They handle constant data, static data that people put some thought into it, and where they know it's correct and where it's probably not too long because otherwise nobody can understand your regex. And so it was only built to be used in a way where the input would be trusted. And so taking regex input is usually generally a bad idea. People still do it. I'll have a screenshot on the next slide. Google does it. JavaScript does it. And probably a whole bunch of other things. And so most of these regex parsers are written in C, and they're really not written for untrusted input. And they have like a whole bunch of nasty issues. I mean, memory corruptions, like all of it. It's really, really ugly. And then, of course, sort of these regular expressions, some of them have features, right? And so Perl's regular expressions have features, for example, where you can embed Perl code in a regular expression. Thank God the Perl developers actually realized this, and they said, well, we know someone is going to use regular expressions as input on their web app while they shouldn't. So what we'll do is we'll turn it off by default for non-constant data. And if you want it, you use this re-eval thing. And then you would think that everybody can at least read a man page like that and, be really careful when they use this re-eval, and that, you would never see these kind of bugs in web applications. So what I did is, I went on SourceForge and downloaded some of these web applications, and it turns out that people apparently don't read documentation because they use re-eval and they take an untrusted regular expression as input, and lo and behold, you get remote Perl code execution. PHP is just as bad. So PHP has two APIs for regular expressions. They have ereg, which is the POSIX regular expressions, and they pass them on to a C API, which does all sorts of ugly things. And they have preg, and these are the Perl-compatible regular expressions, which they use this they use a PCRE library, which incidentally is written by the same guy that made Exim, so you know it's secure, right? But they're supposed to be compatible with the regular expression that Perl uses. And so this preg replace one that Perl uses, right, is sort of a nice one because it has this /e thing, and that means evaluate. And what this means is if something matches in the /e, it gets used as an argument as part of the second argument passed to preg replace, but it doesn't get escaped. So this means or usually doesn't. So what this means is if you're too liberal in your matching, then whatever you're matching against might be PHP code, and it'll get executed. I didn't make PHP, obviously. I think this is awful, but a lot of people seem to like this because a lot of people use this thing, and a lot of people are vulnerable to this stuff. So this is really, really awful. Right, so this is Google taking a regular expression for me. This is just a really long string of like asterisk, dot, and something else. And it tells me, we hit an unexpected error while processing your request. If this keeps happening, please report it. Now I suspect what happens is something blew up on their end, and they're screaming fire and saying, don't ever do this stuff again. But of course I don't really know, because that would be illegal, right? So yeah, this is a prime example of why you shouldn't take regular expressions as input. But hey, who would ever look at this code search thing, right? Seems I'm sort of running out of time. So I'm going to skip this because it's not really that important. Let's see. Right, so I'm going to do a tool release. I wrote a Unix ioctl fuzzer. And for example, I used this fuzzer to find the OpenBSD bug that I demoed earlier. It works in NetBSD, FreeBSD, and Linux too. It's fairly easy to port to a new Unix. Usually takes about an hour or so. The thing is, like, the way these ancient Unixes and most of the BSDs form Unix ioctl codes is really nasty, and it takes some poking around and some tweaking to get that to work well with the fuzzer. Linux was like a walk through the park because they don't have all these ugly ways to form ioctl codes. It's just a big array of numbers. So it's fairly easy to add new Unixes. It takes more or less an hour to add these things. You can download it from this link. I said in about an hour. It'll probably be in about a day because the guy who has to upload this thing, the Digital Dwarf, is here, but he left his SSH keys at home, so he can't really upload it right now. So check it out tomorrow. It'll probably be there. Right. When you compile it, there will be warnings. Ignore them. They might be important, but the fuzzer still works even if you get the warnings. You know, because I'm really not such a good programmer, and I was a bit short on time to actually get this thing to work simultaneously on all different operating systems. So you'll get warnings, but it's okay. You can ignore them. Right. Let's see. I don't want to do this. Right. So that was about my entire talk. I didn't do all of the stuff on my own. I had help from a whole bunch of people. Specifically, I want to talk about BitShifted, because she made my slides, because I could never make slides like this. I'm horrible at creating slides. This was all her. I just create the content. They're not my slides. Thank you. Some useful resources. If you ever download slides, you should look at these things. That was it. Any questions?